In this video, we're going to discuss projections of polyhedra, and we will introduce a method to compute them, which is called the Fourier-Motzkin elimination. Fourier-Motzkin elimination can be seen as the oldest method for solving linear programming problems. However, such method, while it gives you an algorithm, so it's a finite procedure, it is not practical because it requires a very large number of steps. In particular, this number of steps can grow exponentially with the dimension. In any case, we're interested in the Fourier-Motzkin elimination mainly because of its theoretical consequences. The first thing that we need to discuss is the concept of a projection. In low dimension, the concept of projection is very intuitive because essentially it resembles the shadow of an object. For example, here we have a tilted cube in R3, and its projection in its first two components, x1 and x2, is its shadow onto the x1, x2 plane. So let's now formally define the concept of a projection. We're going to first define the projection of a vector and then the projection of a set. So let's pick two non-negative integers k and n with k less than or equal to n. You should think of n as your original dimension and k the dimension where the projection lives. So in the example on the right, we have n equal to 3 and k equal to 2. Now the projection of a vector x, which we denote by pi k of x, is simply defined as the subvector of x that contains only the first k components. So where we just dropped the component k plus 1, k plus 2 until the component n. In the picture here on the right, if you look at this extreme point, of course it lives in R3, so it is a vector with 3 components. Now its projection is this vector down here, which is obtained by just trashing the third component. Now we can use the definition of the projection of a vector to define the projection of a set. The projection of a set S in Rn is denoted by capital Pi k of S, and it's simply the set of the projections of all the points in S. In this definition, to define capital Pi, we also used pi. But of course, you can also obtain a definition of capital Pi that doesn't need that. Such a definition is written below. Pi k of S is the set of all vectors x1, xk, such that there exists component xk plus 1 until xn, such that the vector obtained from x1, xk by appending xk plus 1 until xn, which is x1 until xn, is in S. So it is the set of points in Rk for which there exists a vector in S with the same first k components. It follows directly from the definition of projection that a set is non-empty if and only if its projection is non-empty. In fact, if S is non-empty, it contains a vector x1 until xn. The corresponding vector x1 until xk is in pi k S, therefore it's non-empty. Vice versa, if you have a vector x1, xk in the projection, then there exists a way of extending it with n minus k more components, such that the vector obtained from x1, xk by appending xk plus 1 until xn is in S. Therefore, S is non-empty. Projections of polyhedra are extremely useful for a number of different reasons. For example, here we consider the problem of deciding whether a given polyhedron P is non-empty. So this is not a trivial task in general, and in fact you can show that this problem is computationally as hard as linear programming. But how can we use projections to solve this problem? Well, suppose that we can construct the projection of P into the first n-1 components, which is capital Pi n-1 of P. We just said that P is non-empty if and only if this projection is non-empty. Therefore, we can just forget about the original P and instead solve this problem over this n-1 dimensional projection. Of course, you can repeat this argument until you get to pi 1 of P. So the projection of P onto the first component. This set is therefore one-dimensional because it's contained in R. So we started from the problem of deciding whether P is non-empty, and we understood that it's equivalent to understanding if this one-dimensional object is non-empty. But at this point, the emptiness of this one-dimensional set is easy to check. So how can you do that? So how is this set given to us? It's given to us by means of linear inequalities. Since this set is one-dimensional, it can be described using only inequalities of the form x1 greater than or equal to a lower bound, and inequalities of the form x1 less than or equal to an upper bound. But at this point, the emptiness of this set is very easy to check. Now it is simple to check that this one-dimensional set is non-empty if and only if the largest lower bound that we have is smaller or equal to the smallest upper bound that we have. This method seems to be very useful because it allows us to check non-emptiness of a polyhedron by checking non-emptiness of a one-dimensional set, which is trivial. So where is the catch? The main disadvantage of this technique is that at every step, while we decrease the dimension by 1, a large number of constraints is usually added. In particular, the number of constraints can increase exponentially with the dimension of the problem. If you want to see how this can happen, I suggest that you look into exercise 2.20 in the textbook. So now let's see the details of the Fourier-Motzkin elimination method. This is a method that, given a polyhedron P, computes its projection onto Rn-1. So we are given a polyhedron P in Rn, and this is defined without loss of generality only in terms of inequalities of the form greater than or equal to. So the notation we're going to use is that we have m inequalities indexed by I, and the ith constraint is sum for j that ranges from 1 to n of aij xj greater than or equal to bi. To construct pi n-1, we essentially need to eliminate the variable xn. So here's the beginning of our algorithm. The first thing that we want to do is to rewrite all the constraints in a form that will be useful to us at the next step. Namely, we isolate the variable xn, which is the one that we wish to eliminate. So we keep ain xn on the left hand and bring everything else on the right hand. And this is what we obtain. So now let's consider a few cases. If ain is equal to 0, then the variable xn doesn't appear at all in the inequality, and we have just a 0 on the left-hand side. In the remaining cases where ain is different from 0, we divide both sides of the inequality by ain. Now, if ain is positive, we will have an inequality of the form xn greater than or equal to the remaining part of the inequality. On the other hand, if ain is negative, then when we divide both sides by ain, the sign of the inequality flips and we obtain an inequality of the form xn less than or equal to the remaining part of the inequality. Now we can rewrite all these m inequalities in a compact way by letting x bar being equal to the vector of variables x1, xn minus 1. So as we said, if ain is positive, we have an inequality of the form xn greater than or equal to the remaining part of the inequality, which we can simply write as fi transpose x bar plus di. If ajn is negative, then the inequality takes the form xn less than or equal to fj transpose x bar plus dj. And finally, if akn is equal to 0, we obtain an inequality of the form 0 greater than or equal to fk transpose x bar plus dk. If you're wondering why I'm using j and k here instead of I, this is simply because I want to differentiate the index that I'm using in these three types of inequalities because it will be useful for me later. Of course, all the di, dj, and dk are scalars, and all the fi, fj, fk are vectors in Rn-1. So now, in these new slides, I have simply rewritten what we have just discussed, but I have highlighted with different colors the three different types of inequalities. So in red we have the lower bounds on xn, then in blue we have the upper bounds on xn, and then in green we have the inequalities that don't contain xn at all. Now in the last step of the algorithm we are gonna write down the system that, as we will see later, describes the projection of P. We're gonna call Q for now this polyhedron in Rn-1, and it's obtained as follows. So the green inequalities that don't contain xn at all are simply copy-pasted. This makes sense because this inequality already have no xn whatsoever, so we just copy them. But what about the other inequalities that instead contain xn? Well, we need to write down an inequality that doesn't contain xn at all. And so we're gonna simply pick any upper bound on xn and any lower bound on xn and put them together. So we're gonna write the upper bound greater than or equal to the lower bound. And this is exactly what's written here. And so we obtain one inequality for every pair of inequalities, one red and one blue. By construction, the new system doesn't contain the variable xn at all, so it is in fact a polyhedron in Rn-1. Of course, for now, this is just an algorithm that constructs a new polyhedron Q starting from the original polyhedron P. Soon we will show that Q is actually the projection of P. But first, let's see an example. We look at the three-dimensional problem defined by these inequalities. As you can see, there are only three variables involved. In the first step of the algorithm, we need to rewrite these inequalities according to the coefficient of xn, which is x3. So the first inequality doesn't contain x3, so we're going to write it in this form, and it takes the green color according to our notation in the previous slide. Then the second and third inequalities have a positive coefficient of x3, so we will obtain two lower bounds on x3, and here they are. Finally, the remaining two inequalities have a negative coefficient of x3, and so we will obtain correspondingly two upper bounds on x3. So in the next step, what do we have to do? We're going to keep the green inequality and combine each lower bound with each upper bound. And this is the system that we obtain. As you can see, there's still only one green inequality, which is left unchanged. And then the first upper bound is paired with both the red lower bounds. And similarly, the second upper bound is paired again with both lower bounds. So the polyhedron Q is then defined by this system. Theorem 2.10 then says that the polyhedron Q constructed by our elimination algorithm is equal to the projection capital pi n-1 of P. Let's prove this theorem. In this theorem, we need to prove that Q is equal to the projection pi n-1 of P. So we're going to prove separately the two containments. In order to prove this theorem, we're going to use these two systems that we saw in the elimination algorithm, namely the system star, the first of the two here, which we just obtained by rewriting the original set of inequalities, and the second system double star, which is the one that defines Q. First, we prove that the projection pi n-1 of P is contained in Q. So let's pick a point in the projection, x bar in pi n-1 of P. By definition of projection, this implies that there exists a component xn such that the vector x bar with appended the component xn is in P. Therefore, the vector x bar xn satisfies the system star, since star is the system that defines P. From this, we obtain that x bar alone satisfies double star. Why is that? Well, we only need to check that x bar satisfies the inequalities blue greater than or equal to red. Of course, they're satisfied because in star we have that each blue is greater than or equal to xn and xn is greater than or equal to red. So these two inequalities imply that blue greater than or equal to red. Now double star is the system defining Q, so we have shown that x bar is in Q. Next, we prove the other containment, namely that Q is contained in the projection. So let's pick a vector x bar in Q. Q is defined by the system double star, and in particular, since in the system double star we have all the inequalities of the type blue upper bound greater than or equal to red lower bound, then the minimum of the upper bounds must be greater than or equal to the maximum of the lower bounds. So this is the minimum among the upper bounds, and we said that this is greater than or equal to the maximum among the lower bounds, which we can write as max. Now we're almost done. We only need to pick any number xn that lies between the min and the max, and we will have that x bar xn satisfies star. Let me write it. This implies that x bar xn satisfies star. Star is the system defining P, so this implies that x bar xn is in P. And by definition of projection, this implies that x bar is in the projection n-1 of P. So we have shown also the second containment, and this concludes our proof. Let's get back to the slides. Thanks to theorem 2.10, now we know how we can construct the projection pi n-1 of a polyhedron P. Applying this technique recursively, we can then construct pi n-2, pi n-3, and so on and so forth until pi 1. This follows because the projection pi n-2 of a vector x is clearly equal to pi n-2 of pi n-1 of x. And accordingly, the projection pi n-2 of a polyhedron is equal to pi n-2 of pi n-1 of P. Therefore, applying the elimination algorithm n-1 times, we obtain the set pi 1 of P. Unfortunately, every application of the elimination algorithm can increase the number of constraints substantially. In the worst case, if the number of inequalities is an even number m, then half of them could be blue and half of them could be red. Therefore, the obtained system will have m divided by 2 times m divided by 2 constraints. So at every iteration, the number of constraints can essentially increase quadratically. And this implies that even though we can apply this algorithm recursively to obtain pi 1 of P, this polyhedron could be described by a very large number of constraints. Of course, almost all these constraints will be redundant because pi 1 of P is one-dimensional. Therefore, it is either empty, or it's a point, or a segment, or a half line. So you always need at most two linear inequalities to define it. But in general, to find these two linear inequalities, you need to look at all of them. So from an algorithmic point of view, the Fourier-Motzkin elimination is not so effective. And in fact, it's not really the reason that we're studying such an elimination algorithm. The true reason we're studying it is because of its theoretical consequences. So what are these theoretical consequences? Note that the elimination algorithm always produces a polyhedron by construction, because the output is the polyhedron Q, which is defined by finitely many linear inequalities. Furthermore, any projection pi k of P can be generated by repeated application of the elimination algorithm. These two facts together imply that for a polyhedron P, the projection pi k of P is always a polyhedron for any k. Let's state this formally. Let P be a polyhedron in Rn plus k. Then the projection onto Rn, which is the set of points in Rn for which there exists a y in Rk such that xy is in P, is also a polyhedron. And we're going to immediately put this corollary to use. If you remember, when we discussed the alternative representation of a polytope in terms of the convex hull of finitely many vectors, I promised you that we would prove that the convex hull of a finite number of vectors is a polyhedron. And now we can do this very easily. In fact, by definition, the convex hull of a finite number of vectors x1 until xk can be written as follows. Is the set of points in Rn for which there exists a lambda in Rk such that x lambda is in the polyhedron P defined as follows. P is the set of points x lambda such that x can be written as the sum of the lambda I xi and the sum of the lambda I is equal to 1 and lambda greater than or equal to 0. So the convex hull of x1 until xk is the projection of the polyhedron P onto Rn, while the polyhedron P lies in Rn plus k. Thanks to corollary 2.4, we can now argue that the convex hull of x1 xk is a polyhedron. So far, we have seen how the elimination algorithm can be used to understand if a polyhedron is empty or not. But now I also want to show you how it can be used also to solve linear programming problems. So we consider a linear programming problem, minimize C transpose X, subject to AX greater than or equal to B. This is a general linear programming problem. The idea is now to define a new variable that we're going to call x0 and which corresponds to the cost of a solution. So we now look at the polyhedron given by the vectors x0, x, such that ax greater than or equal to b and x0 is set to be equal to the cost of x, so equal to C transpose X. Clearly this is a polyhedron because all the constraints are linear. Now, assuming that the original vector x is n-dimensional, we have that our new polyhedron is of dimension n plus 1. What we want to do next is to use the elimination algorithm n times to eliminate all the original variables x1, xn. So essentially we want to obtain the projection onto the space of the x0 variable. Such a projection is then, by definition, the polyhedron Q, which is the set of points x0 for which there exists a vector x in Rn that satisfies Ax greater than or equal to b and x0 equal to C transpose X, which means that x0 is the cost of the vector x which was feasible to the original linear programming problem. Note that the polyhedron Q is one-dimensional, and clearly the optimal cost of the linear programming problem is equal to the smallest element of Q. Therefore, using the elimination algorithm, we were able to recover the optimal cost of the original linear programming problem. However, in linear programming, we're normally interested not only in the optimal cost, but also in an optimal solution. So the next question is, can we also find an optimal solution to the linear programming problem? And the answer is yes. Such a solution can be recovered by backtracking. Essentially, to recover such an optimal solution X, you need to apply the same idea which we saw in the second part of the proof of theorem 2.10. I encourage you to try to use the same idea that we used in that proof in order to find an optimal solution X of our original linear programming problem. The idea of backtracking that we saw in the proof only allows you to recover one variable at a time. So what you should do here is start from the n plus 1 dimensional polyhedron that we defined here, and then consider all the n polyhedra that you obtain by eliminating one variable at a time, as we previously discussed. At the very last step, we obtain the optimal cost, which is a point in Q, and then we can backtrack one polyhedron at a time and recover one by one all the components of an optimal solution. And this concludes our video on the Fourier-Moskine elimination, And it also concludes our chapter 2. In the next video, we're going to start the next chapter, which is about the simplex method, which is one of the most successful algorithms to solve linear programming problems.